Hey you guys, in the last video we covered binary search, which is one of the more effective searching algorithms. However, it comes with a drawback that the array needs to be sorted, which brought up another question on the subject of sorting. If you have an array or a vector of data and we don't know the exact order of the contents are, we just know that it's not from low to high or from high to low, how can we go about sorting it? What are the best algorithms that we can use to sort an array? Well, this seems like a simple question. This is actually a very complicated one, and it is a result of many years and decades of studying data structures and means of sorting. But here I'm just going to introduce one of the algorithms called Insertion Sort, and how it works in a nutshell is that Insertion Sort partitions the array into two sections: the sorted part of the array and the unsorted part of the array. It goes one by one and inserts the first element of the unsorted part of the array into wherever it's supposed to go in the sorted part of the array, right? So we take the first element of the unsorted and we insert it into the sorted part of the array, hence the name Insertion Sort. Well, it seems like I'm talking about two different arrays. This is actually done in the same array itself. So it's an in-place algorithm, meaning when we run this sorting algorithm, we don't need to create any other arrays or any other vectors. We can use the same one that we got. So why don't we take a look into the main that I have here. I have a print vector function. It's just a general function to print the contents of a vector. Here I have my vector x, and what I'll do is that I will print out the contents of x, and it's a function call, not an operator overload, print vector of x. And then I'm going to go and call, I'm actually going to repeat this twice. And here I'm going to call my insertion sort function, which will take the array or vector itself and it'll sort it without needing to return another vector. So here's how I'll go about implementing it. So I want it to be a general algorithm, even though I'm only using templates. So I'll have my type name, I'll say t void insertion sort. Let me make sure, yeah, that it's all spelled correctly. So this is just going to be a std vector of data type t, and we're going to get a reference v. So it's not const, unlike some of the other algorithms that I've been using before, like linear search and binary search and print vector. That is because we're going to be sorting our array v here now, and in order for us to sort this array in place, we need to change the data that's inside of v. So this can't be, const. So what I'll do here is that first I'll create a size variable to have the size of the vector, and then I'm going to start with two for loops. It's going to be a for loop within a for loop. So I'll start with for int of I equals 0. I is less than our size, the size of our vector, and we're going to be incrementing by 1. And this is going to go through, actually, this should be equals to 1. I should be equals to 1 here because when we begin with insertion sort, the very first element of v, which is going to be v of 0, that's going to be considered our sorted part of the array, while the n-1 or the size -1 elements of the vector are going to be the unsorted. So v of 1 is going to be the first element of our unsorted algorithm, and we're going to insert it into or swap it with our sorted part of our array. So I plays the role of iterating through our unsorted part of our array and swapping it or inserting it into the sorted part of the array. So we're going to have our int j, and this is going to be equal to 0 because we can insert our first element of the unsorted array at the beginning of the sorted array or anywhere else. So I'm going to say j is equal to 0, and I'm going to say j is less than I, because in our array from between 0 and I, that's going to be our sorted part of the array, and I don't want to go forward. And then I'll continue by incrementing by 1. Now what I'm going to do is that I'm going to be sorting from low to high, so I'm going to be checking if v of I is less than v of j. Then if it is, we're going to swap the two values. So I can write my own swap function, which would kind of look like this. Right, here's the swap function where I use an additional variable to swap these two. Or I can use the standard template library. So I can use a function called stdswap, and I can swap v of I with v of j. And effectively, this function does exactly what I've just written above. If I remember correctly, this is the implementation of stdswap. This is just my own. I just rewrote it. But stdswap effectively does what my own swap function does. It's going to exchange v of I and v of j with each other, and that's how it's going to sort it. So again, let's talk about the iterators. I is going to iterate through the unsorted part of the array one at a time. So the first index in which my vector is going to be unsorted is going to be at index 1, while the sorted part of the array is going to be only v of 0. And the second for loop here, j, is to make sure that when we do the swap, everything is in order. So when I insert it, I may need to slide some values to the right or to the left, and this j for loop helps me do that. And its bounds start from the beginning of the sorted part of the array up until the end of the sorted part. So when I equals 1 here, the only sorted part of the array is 0 and only checks if I need to swap with 0. Once this increments to I equals 2, that means that indices 0 and 1 are part of the sorted part of the array now. So our inner for loop j is going to go from 0 to 1 and insert whatever v of 2 is into the sorted part and make sure that it's going from low to high. And if this doesn't make too much sense, don't worry. In the next video, I'm going to cover visualization where it should clarify this much better. With that being said now, let's double check main to see if it's ready to go, and I think it is. So it's ready to go, and why don't we go about compiling our function now. Good, it compiled with no errors, except for me making a typo there. And look, our algorithm is sorted, which this isn't too bad, right? It's sorted from low to high, so we get our what seemingly is random vector, and now it's sorted onto here. And let's say if I want to use linear search or binary search, I should be able to use either of those, mainly binary search, without any problems now. So let's talk a little bit about the computational complexity of our insertion sort. Always, this for loop is going to be going from 1 to size minus 1. So if we have a vector of length n, this for loop will loop n minus 1 times. If we go here, in the worst case scenario, what will happen is that this can go always from 0 to I, and I will eventually grow to n. So in its worst case scenario, meaning way at the end of it, it can loop n minus 2 times. It can go from looping just once, and then when I is 2, it can loop twice. If I is 3, it can loop 3 times, up until I is equal to n minus 1, where our inner loop can loop n minus 2 times. So in the worst case scenario, our outer for loop, which has the integer I, can loop n minus 1 times, and our inner loop j can loop, at worst case scenarios, n minus 2 times. And if you look at this at a large scale, we typically drop the constants, right? So the subtraction of constants. So it's essentially n times n. This means that now in the worst case scenario, which for insertion sort would be if our vector was from high to low, because we're sorting it from low to high, our worst case scenario would be if our vector was high to low, because it'd have to keep swapping and it'd do the maximum swaps, which would give us around 25 loops. That's an n squared algorithm. It's a quadratic runtime. So this algorithm scales faster or grows faster than our linear algorithm, linear search. And that's bad because we want things to scale slowly. So as our size of the vector grows, the loops that it'll take to sort the vector will grow by multiplying itself. So in the worst case scenario here, I have a vector of 5 elements. So it would take at most 25 loops to sort this array. However, if I have an array of 6 elements, it will take 36 elements. It will take 36 iterations of the worst case scenario to sort that array. And going from 25 to 36 with a difference of 1, that's a pretty big jump, and it only gets worse as the array grows. So insertion sort is kind of a little bad, but if you use it for a small array, it's not too bad, which is typically what you'd use insertion sort for. You'd use it for a small array, I don't know, probably less than 10 values. I'd probably use insertion sort for just because at that point it's not going to be too bad compared to, other bigger possible algorithms. But in terms of sorting, let's say something that's like 10,000 items long, I would never use insertion sort. I would use another sorting algorithm. So in the next video, we're going to cover our visualization of insertion sort, and then we're going to talk about another algorithm, which is faster than insertion sort and should be used with larger arrays called merge sort. And I'll see you there.